Um, Before we start,
Yeah,
sir, do you have any recommendations for books and things that might increase my knowledge of the thesis
which
topic?
aspect? Well, yeah, for quantum information, I would look at uh, Nielsen and Chuang, chapter 2.
Sir,
That's a good.
could you
Yeah,
repeat that?
I'll write it. Just one second.
Okay, thank you.
Just a- All right. Okay. Can you hear me?
Yes, sir.
Okay, just give me 1 second. All right. So the reference, right? So the reference is going to be. mm, So for introduction to quantum information, the reference is Nielsen. Is Nielsen? No, Nielsen is like, I think. Uh, Nielsen and Chuang. It's a very standard book. It's quantum information. What I forget the name, but I would say chapter 2 is a good way of getting into the subject. So it's a very basic review of quantum mechanics. So yeah, have a look, and then we can, if you have questions, we can discuss that. Okay.
Okay, thank you.
So last time we discussed tensor products. So a tensor product is nothing but just product, right? So if I have, say, a quantum system, say a particle whose wave function is given by psi x1, and another particle whose wave function is given by phi of x2, and there's some time dependence, then the combined system is described by some tensor product of those two. Let's call it, say, chi, and that'll be a function of both x1 and x2. And that'll be given by initially by something like this. And if there's interaction, there might be some entanglement. So we talked about tensor product, and in the abstract, we discussed, suppose we have a quantum system quantum system say A, and which is described by a Hilbert space H of A, and a quantum system B, which is described by states in Hilbert space B, HB, right? So a tensor product of these two of these two spaces can have states such that A1, you take A1 from the first Hilbert space. So this is a vector. And you take, say, B1 from the second Hilbert space. And then, A1 cross B1 is a tensor product which lives in HA cross HB. Now, if I choose EIA to be some basis that spans HA, spans mean it provides a linearly independent basis. And suppose I take EIB to be a set of basis vectors and they span H of B, then of course I can express my vector A1 as a linear combination in terms of EIA, and the coefficients are, say, A1I, and similarly, my vector B1 in terms of the basis vectors, say, E, I, B. Here I is, tells you what the which of the basis vectors we are talking about. This is telling me what system it is, and this is telling me the component of that vector in that basis, okay? So it's like, in 3 dimensions, if you have a vector A and we express it as AI, I hat, where I hat, J hat, K hat, sorry, I should really be more explicit. A is equal to, say, AXI plus B, sorry, not B, AYJ, and then AZK. So the IJK, these are the basis vectors. These are analogous to these things. And these are the components, and they're analogous to this, okay? Any questions?
Sir, are those notation standard notations or considered as standard notations? Sorry?
I'm making it up, and I'm going to ditch this notation very soon. So,
Yes,
yeah, you just think of the concepts here. Don't get too attached to the notation, okay? I'm just writing this notation because what I want to say is that if you have chosen your basis, then this vector can be thought of in terms of the components, and this vector can be thought of in terms of its components, right? So if I give you what basis is, then if I tell you what the components of that vector is, I'm giving you the whole vector. Do you agree?
Yes, sir.
Yeah. So now the point is that I want to find out what the components of this vector is. So the thing is that the dimension of the Hilbert space HA is, say, I don't know, like NA, and suppose a dimension of the Hilbert space HB is, say, NB. That means EIA, how many vectors are there? I goes from 1 to NA, right? And with EIB, I goes from 1 to NB, right? Because these are the basis vectors, and there has to be the number of independent basis vectors have to be equal to the number of the dimension of the space. Right? So now, what is the dimension of HA cross HB? Well, it's actually NA times NB. Here, this is just multiplication. And why is that? Because if I look at the basis vectors in this space, these are just EIA cross EIB, EJB. So how many? So I takes the value from 1 to NA, and J takes the value from 1 to NB. So the total number of vectors, independent vector, is NA times NB. So that's a dimension of the product, or the Hilbert, or the tensor product. So what is the, what are the components of this, tensor product? Well, in this basis, it's nothing but A1I times B1J. Okay. All right. So, and if I have now some, linear operator acting on the Hilbert space, so it sends vectors from HA to HA. So a linear operator, if I now express it in the basis, so if I now say I take EI, take its Hermitian conjugate, and multiply it from the left, and EJ, and then this defines the elements of a matrix, which I call Aij. So this is basically the representation of this linear operator in this basis. Okay, so that when A acts on some vector and gives me, say, another vector A prime, in this basis, this equation reads like the following: A, the matrix Ij, acting on the column vector J, where we are summing over J, gives me the column vector A, its element I. So this is a matrix multiplication, right? There's a linear transformation. So a linear, operator becomes just a matrix in a particular basis. So now if I look at my tensor product, say I have my AB, and suppose that I apply the linear operator A on A and the linear operator B on B, then and I get, say, A prime cross B prime. Then in terms of components, what I'm doing is I'm just taking AI, sorry, let me call it something, sorry. Yeah. I'm just saying AI of J, A of J, and there's a sum over J, B, KL, where it's a sum over L applied on L, is going to give me A prime of I times B prime of K. Okay, so this is how operators act on tensor products. So we will soon be doing some explicit, calculation. So don't worry too much if this looks too abstract to you. Okay. But do we have any questions? Because questions will help us. Okay. All right, if there aren't any questions, let me move on to my next discussion. And the next discussion point is entanglement. Are you guys familiar with the idea of entanglement?
Very vaguely.
Okay, good. So let's then go over. So now let's switch our notation. As I was saying, I was going to switch to the standard quantum mechanical notation. switch to, say, a more quantum mechanical notation. So suppose that psi I of A, subscript A, is some state in our Hilbert space HA, and say phi I of B is a state in our Hilbert space H of B. So then the state, say psi 1 cross phi 1 is not entangled, okay? It is a separable state. Okay, but the state, say psi 1 tensored with phi 1 with some constant coefficient C1 plus C2 for, say, psi 2 cross with phi 2, where C1, C2 are not 0. This state is an example of a non-separable state or an entangled state, okay? Okay, so basically what we're saying is that we have states which are the most simple tensor products, but if I add, but this is an element of a vector space, right? So we can take another element of this vector space and add them together. And if that sum cannot be written like this, then it's an entangled state, as simple as that, okay? So mathematically, it's a very simple thing. It's something that we're allowed to do on a Hilbert space, but physically it has profound, consequences, okay? So, states which are of, right. So states which are of the form of, say, 1 over square root of 2 psi 1 cross phi 1 plus some phase e to the power I of theta. So it's a constant phase, not a function of space-time. If the entanglement is of this form, entangled state, meaning that what is important here is the fact that we have 1 over square root of 2 pi, and here we have something which is also 1 over square, proportional to 1 over square root 2 pi, where the proportionality constant is a phase. States of this form are called maximally entangled. Okay? Because we shall see that when the coefficients are of this, of this modulus, then the states have the most amount of entanglement possible. Okay. So states which are, which are entangled over two systems are called bipartite states. Okay, bipartite means it has two parts. Okay, any questions?
No, sir.
Sir, I have one.
Yeah.
psi 1 cross phi 1 আর এইটা একটা আমরা কি এটাকে একটা সিস্টেম ধরছি আর হচ্ছে কি psi 2 এবং phi 2 কে ক্রস phi 2 কে এটাকে আরেকটা সিস্টেম ধরছি?
No, no, no. Yeah, no, that's not the case. So let me just show you. Suppose you have one system, one particle. You can have a state psi 1, and you can have a state psi 2 of the same particle, right? They're different states, right? And then you can take a linear combination of these, right?
Yes, sir.
And that is also a possible state of the same system, right?
Yes, sir.
Now, what we're doing is that we have two particles, A and B. We are bringing them together in a bigger system. And this system has its own state, say psi 1 cross psi 2. But it can also have another state, sorry, psi 1 plus phi 1 times phi 1. But it can have another state which is psi 2 cross phi 2. Just as this guy could have this state or this state, this.
Oh, now I get it. Yes,
Yeah,
sir.
can
Sorry,
have this
sir.
state. But these are also elements of the big Hilbert space.
Yep.
So we can, by the rules of quantum mechanics, we can take linear combination, and that will still be a state of the system, combined system, right?
Yes, sir.
So that's what we're doing. Okay, so if you like, here, this is a subsystem, this is a subsystem, this is another subsystem, this is another subsystem. So often, one will write this A and this B here, this A here, this B here, to make it clear. But from the context, these should be clear even if I don't write it, okay? All right, any more questions? Okay, so discussing these ideas, it's very, very useful to have a very simple system where a lot of these ideas are very explicitly manifested. And so let's take the most non-trivial quantum system, and that system is called a qubit. Okay, so qubit is short for a quantum bit. So in discussion about quantum systems, two-level systems are a great tool. So two-level systems. So examples of two-level systems are, say, the spin of a spin half particle and its spin degree of freedom, okay? So for example, if I have an electron, it can be in a spin up or a spin down state with respect to a certain observable as Z. And that's an example of a two-level system. There could be other two-level systems, such as, say, suppose you have a, like the lowest, say, levels of an atom. Okay, so for example, if you have an atom, suppose that it's got some energy states, and then suppose that you say, okay, I'm going to take the lowest energy state, which is, say, E0, and like, sorry, let me just make sure we are not being disturbed. All right. So The lowest level is E0, and then then the first excited is E1. And suppose that we can make sure that the energy, the photons coming into into the system is such that the excitation, the energy of the photon is less than E1, not less than, but equal to or less than E1, E0. Then the only transitions that will occur is between these two states, right? So all the higher states, we can ignore them for the time being. So this is another experimental realization of a qubit. Okay, so there are many different realization of qubits. Another one is another one would be an interferometer. So for example, you have a half silvered mirror, and you have a photon coming this way, and the photon can get reflected and go this way. Say this is the path A, or the photon can go through here, and this is path B. And this is also a qubit. Okay, so the two paths are two different states of the same quantum system. Okay, so interferometer. So these are the different ways of realizing a qubit. Okay, but of course we are not interested in experimental realization here, but I think it's good to know what these experimental realizations are. So suppose we have a qubit, then its basis vectors are usually denoted by ket0 and ket1. And this is known as the computational basis. Okay, so for example, if you're looking at spin, and our degree of freedom that we're looking at is the Z component of the spin, then of course the spin up state is what we're going to call the, say, 0, or the other way around, doesn't matter. Just 1 second, okay? Hello? Walaikum salam. Ji. আপনি নিয়ে আসছেন? হ্যাঁ, অসুবিধা নেই। হ্যাঁ, আপনাদের যখন পারবেন তখনই নিয়ে আসেন। হ্যাঁ, অসুবিধা নেই। থ্যাংক ইউ। হ্যাঁ। Okay, bye. I'm sorry about that. Yeah. Okay, let me go back to my. All right. So this is going to be, say, 1, or the other way around. It doesn't matter. Okay. What we call, so so this is called the computational basis. That's really what's important. Okay. So now, of course, this is called a bit in analogy with classical computing. But in classical computing, the allowed, say, states of a circuit are only zero and one, right? In computer science, that's all you're allowed. That suppose you have a NOT gate, right? If you go 0, 1 comes out. If you 1, then 0 comes out, right? But in quantum mechanics, for a qubit, your two-level system can be in the state which is also a linear combination of this of the computational basis, right? And quantum mechanics allows that, right? So, where C1 and C2 are constants, are complex constants, right? So in quantum mechanics, a qubit may have an infinite number of states because C1 and C2 are continuous objects. They're numbers, right? So they're complex numbers. So let's look at this. Let's look at the space of possibilities for a qubit, or what the Hilbert space looks like. So we're looking at the Hilbert space of the qubit. Now, because our states are being normalized, so 0, this is 1, this is 1, this is 0, right? So this is an orthonormal basis. And if we assume that our state psi is also normalized, this implies that the constants must satisfy this constraint, right? Is that clear?
Yes, sir.
Okay.
Yes, sir.
So now, since C1 and C2 are complex numbers, we can combine them in a two-dimensional vector, say C1, C2, and now it takes the value in a two-dimensional complex plane, right? But because of this condition, if we break them up into real and imaginary part, it would seem like that, that C1 and C2, take value in a three-dimensional sphere, right? Because this is the equation of a three-sphere.
Yes, sir.
Yeah, but it's actually not true. And the reason is, we have normalized our state, but quantum mechanics tells us that two states are physically equivalent if they're proportional to each other, right? So but if we normalize it, do we fix this constant completely? That was a question. What do you think? So is C1, if I impose, this condition? Oh, sorry about that. Hello? ওয়ালাইকুম আসসালাম। জি বলেন। জি। হ্যাঁ, আপনি বন্ধ করেন, আপনারা কালকে যখন খুলবেন তখন দিয়েছেন। হ্যাঁ, নো প্রবলেম। হ্যাঁ, আচ্ছা, থ্যাংক ইউ। হ্যাঁ, ওকে, বাই। হ্যাঁ, ওকে। Oh, sorry, police is making problem for Mina Bazar employees. All right, so the question is, if I impose this, does that fix this constant to be, say, 1? No, it doesn't. It just, fixes
Summation. Yes.
No, there's no summation. What I'm saying is that it can be a phase, right? I mean, this state gives me this, but if I redefine this state to be e to the power I theta of psi, then this state, so let's call this, say, psi prime. Psi prime is equal to psi, equal to 1, because this is just a phase, and the phase drops out, right?
Yes, sir.
So the fact that we have normalized it still, means that there is an arbitrary phase freedom that we have not used up. So we can use that freedom to fix C1 to be a real number. Okay? So it's only the relative phase between C1 and C2 which matters. And we can choose C1 and C2 now to be cosine of theta by 2. And because we are allowed a relative phase, e to the power I phi sine of theta by 2. You can verify very easily that C1 squared plus C2 squared is 1, right? So this parameterization is goes with the fact that theta goes from pi to 0, whereas phi goes from 2 pi to 0, where 2 pi and 0 are identified. So phi is actually on a circle. Okay, so do you agree that we are allowed to choose this? Then now I want to show that this actually gives you a sphere. So let's write our psi again. Psi is going to be cosine of theta by 2, 0, plus e to the power I phi sine of theta by 2, 1. This is the most general qubit state that we can have. So for example, when say theta is 0, we just get 0. When theta is pi, we get, what do we get? We get, well, theta pi and phi is 0, we get 1. Right? Because when theta is pi, sine of pi by 2 is 1, right? And phi is 0, so this is 1. And when theta is 0, but when theta is pi, cosine of 90 degrees is what? Is 0, right? And the most maximal entangled state is going to be when it's between the two, when theta is pi by 2. When theta is pi by 2, phi is going to be 1 over square root of 2 of 0. Not, sorry, maximal entangled. Anyway, sorry, I misspoke. This has nothing to do with entanglement yet. Okay. Okay, so is this clear now? The most general qubit state can be written like this.
Yes, sir.
I mean, the choice of half here is kind of arbitrary. If you change the choice of half here, these ranges will change. The choice of half here has to do with something that is coming up. And the idea is that we can think of this state as being a point on the surface of a two-dimensional sphere. Okay? So it's a sphere not in physical space, but in mathematical space. Actually, this sphere is going to be the Hilbert space. And so this is, I'm going to call it the, okay. So this is the z-axis, but this north pole, I'm going to associate the north pole with 0, the state 0. And the south pole, I'm going to associate with 1. And any point on this sphere, so now this is one axis, another axis. So any point on the sphere, so it's going to have a polar angle and an azimuthal angle, right?
Yes, sir.
So it's going to have, and that polar angle is going to be theta, okay? And that azimuthal angle is going to be phi. So that, these angles, theta and phi, they are telling you where on this sphere, on the surface of this sphere, your state lies. So for a qubit, we see that we have a whole sphere's worth of states. So for a qubit, we have a whole S2 worth of states. Actually, we shall see that we have more than that, because we shall see soon that the inside of the sphere also has an interpretation, okay? And that's something we will soon see. And so this sphere, with its inside included, has a name. It's called the Bloch sphere. And it's named after, I think his name is Felix Bloch, the famous Soviet physicist who got the Nobel Prize for NMR, along with Henry Purcell. Okay. So now for the last thing, let's discuss the entanglement of qubits. Okay, so now suppose we have two qubits, A and B, and they're in some maximally entangled state. I'm going to call it psi 1. Okay, where 1, 0 by 1, 0, we mean 1A cross 0B, and 0, 1 is 0A cross 1B. Okay, so this is a shorthand notation. The first position is the position of the A qubit, and the second position is the state of the B qubit. Okay. Okay, now consider these two particles to be in such an entangled state, and suppose that particle A, the first particle A, ends up in Alice's lab. And the B particle ends up in Bob's lab. Okay. Or it can be Aisha and Bilal. So, but they're still in an entangled state, these two particles together. Now, suppose that Alice, makes an experiment, or makes an observation in the computational basis. What does this mean? This means that she is she has, her observation consists of these two projection operators. So she's either going to get 0 or 1 as a result of her observation, okay? Now the question is, what is going to be the subsequent observation made by Bob? Okay, can someone tell me? So we are in this state, and suppose Alice makes an observation and she finds that her particle is in state 0. So what is going to be Bob's observation if Bob makes a subsequent, observation on his particle? Will it be 0 or 1? Why don't you guess?
1.
Yes, it will be 1. And the reason is when Alice, makes an observation, what happens is that the state collapses from psi to one of these states, because she is observing in the 0-1 basis. So if Alice observes 0, then it collapses into this state. If Alice observes 1, then it collapses into this state. So this goes into either, say, 0-1, or it goes to 1-0. If you believe in the many-world interpretation of quantum mechanics, you would say that, this was before Alice made the observation. As soon as Alice, made the observation, the universe, branched into two different branches. In one branch, Alice has the state, the combined state is 0-1, and in another branch of the universe, this. So this is the many world interpretation. Okay. Have you heard of many world interpretation?
Yes, sir.
Yeah. So this is as simple as that. Okay, but we are not talking about interpretation here. Alice. Now, if Alice observes this, then Bob's observation is determined, right? Bob is going to get 1. If Alice observes, say, 0, then Bob observes 1. If Alice observes 1, then Bob observes 0. So, in other words, Bob's observation is conditional on Alice's observation, but only if Bob observes in the computational basis. If Bob does not observe in the computational basis, then it's a bit more complicated. Okay, so we are not going to go into that now. So Alice, again,
Sir,
yeah.
is this only true if the states are maximally entangled?
No, it's true whenever it's entangled. If it's maximally entangled, it just increases the chances. The chances by which Alice gets one state or the other will depend on the coefficients, right? So, for example, if this was, say, different, if this was some other constant, say C1, C2, then if Alice makes an observation, then the chance that Alice gets 0 is C1 squared, and the chance that Alice gets 1 is C2 squared, right? So it just changes the probability. But of course, Alice will get either 0 or 1. Okay?
Okay, yeah.
So, yeah, so Alice gets 0. If Alice gets 0, then Bob measures 1. And if Alice gets 1, then Bob measures 0. Okay, so there are other, so 2 qubits.
স্যার আমার একটা question, এটা কি স্যার মানে একসাথে সাইমালটেনিয়াসলি হচ্ছে কি অবজার্ভ করবে যদি
Simultaneously
মানে
observe করা দরকার নাই, one can observe after the other. Simultaneously observe করলে একই জিনিস হবে। তখন কে আগে অবজার্ভ করছে, কে পরে অবজার্ভ করছে, এটা ম্যাটার করবে না। There's actually a tension here with special relativity that we will explore later. Because special relativity tells us that simultaneity doesn't exist. That it's a frame dependent thing. So if they were to do the if they were to observe at the same time, there will be some reference frame in which Alice does the observation before, and there'll be another frame of reference in which Bob does the observation before. So the whole collapse hypothesis that one's measurement collapses the wave function for the other becomes a problematic statement. But those are more advanced philosophical foundational issues that is outside the scope of this lecture at this moment. But that's a very good question.
So we can't really say whose measurement is predetermining whose subsequent measurement.
You can if they are time-like separated. But if the measurements are space-like separated, then you can't.
Okay.
Because if there's time-like separation, then of course there's a very clear time ordering, right?
Yeah.
That's what it tells us that time. But if they're space-like separated, then special relativity tells us that there is no absolute ordering. It depends on the reference frame.
Yeah.
Okay. So for these 2 qubits, the combined Hilbert space will be 4-dimensional. And the state that we saw, which was what was it? 0, 1 plus 1, 0. And that forms part of a basis for this 4-dimensional Hilbert space. The other states are 0, 1. It doesn't matter what minus 1, 0. And then say psi 3 is 0, 0 plus 1, 1. And then psi 4 is 0, 0 minus 1, 1. Okay, so they form in orthonormal basis for this 4-dimensional Hilbert space, and together this basis is called the Bell basis. Okay, named after John Bell. Okay, so I think maybe it's a good place to stop for today and discuss some questions that you may have, either from here or the papers.
I've been looking at the out of time order correlator paper, and I'm having a bit of trouble understanding like the definition of it, like at the very beginning, like what it actually means.
Means what? The OTOC?
Yeah.
Right. The OTOC is so it's a thermal. Okay, I guess the definition there is given, right? But it's a measure for chaos, essentially, quantum chaos. If the OTO, so the OTOC typically has some sort of time dependence. And if that time dependence has an exponential dependence on, has an exponential, nature, then it was proposed that such systems have some sort of quantum mechanical chaos, version of chaos. And this was shown in a very old paper on superconductivity. So, okay, let me also bring up the paper, because that way we can so let me see if do you have the paper handy? Because I think I have to find it on my computer or online, right? Hang on. Quantum chaos.
So should I send you the mail? আপনাকে মেল করেছিলাম এই পেপারগুলোকে।
No, I mean, I can find it online. Don't worry. Let me just stop sharing this, then we can. I'm going to just stop this recording, because I think the lecture is the only part I'm interested in.